Hello everybody, my name is Iman. Welcome back to my YouTube channel. I have missed you all very much. It has been a while since I've uploaded a video, but school, work, life have been extremely hectic and demanding. However, things have been calming down a little bit, so I'm excited to be back and I'm ready for us to cover Chapter 4 for General Chemistry. Now, Chapter 4 is titled Types of Chemical Reactions and Solution Stoichiometry. And the objectives that we're going to cover in this chapter are the following. First, we're going to discuss water and its importance. Water is not just essential for life as we know it, but it also holds immense importance as a common solvent in many chemical reactions, especially in our chemistry class. So here we're going to elaborate on the chemical properties of water. How does its structure make it such a versatile solvent, and what types of reactions does it commonly participate in? Then the second objective, we're going to begin talking about the nature of aqueous solutions. Here we're going to learn about electrolytes, strong and weak electrolytes as well as non-electrolytes. Then our third objective is on the composition of solutions. In this section, we're going to dive into the concept of molarity. Molarity is a measure of the concentration of a solute in a solution or any chemical species in terms of amount of substance in a given volume. We're also going to cover the topic of dilutions, which involves adding more solvent to a solution to decrease the concentration of the solute. We will obviously elaborate on both of those in this objective. Then the fourth objective, we're going to learn that there are three main types of chemical reactions: precipitation reactions, acid-base reactions, and oxidation-reduction reactions. We're going to focus a lot on precipitation reactions, a little bit on acid-base reactions, but in later chapters, we will elaborate even more on acid-base reactions. We're not going to touch on oxidation-reduction reactions here at all, but again, we will have later chapters that will dive into that topic. Then our fifth objective, this is going to lead us to start to talk a little bit about acid-base reactions. Really, what we're going to do here is we'll define acids and bases. We'll learn how to identify strong acids and strong bases. And also, we will discuss solubility rules here. These rules are going to be really important for this chapter because they're going to help us predict which compounds will be soluble in water and which won't. Next, we'll talk about precipitation reactions. Again, the key to predicting whether a precipitation reaction will occur is going to lie in our understanding of the solubility rules. So you will quickly learn that that is a very important topic to master in this chapter. And those rules are going to help us predict whether a precipitation reaction will occur when two solutions are mixed. Then our seventh objective is about describing reactions in solutions. Here we're going to learn about net ionic equations. Net ionic equations are a useful tool in chemistry for simplifying and representing reactions. Essentially, they show only those chemical species that are directly participating in a reaction, while kind of omitting ions that don't participate in the reaction. So we're going to learn how to write net ionic equations. Then in the eighth objective, we're going to connect the stoichiometry concepts we learned in the previous chapter to what we will learn about precipitation reactions to solve some problems together. And then last, but certainly not least, we're going to do the same thing by connecting the stoichiometry concepts we learned in the previous chapters to what we'll learn about acid-base reactions, specifically focusing on titrations. And we will elaborate on what titrations are. Now, with this introduction out of the way, now that you know the objectives that we're going to cover, let's go ahead and get started with objective 1, water. Much of the chemistry that affects each of us occurs among substances that are dissolved in water. So, for example, virtually all the chemistry that makes life possible occurs in an aqueous environment, so in water. Also, various medical tests involve aqueous reactions, and they depend heavily on analysis of blood and other body fluids with water present. Now, aqueous chemistry is also important in our environment. So, in recent years, contamination of the groundwater by substances like chloroform and nitrates have been publicly talked about. And water is essential for life. And so, maintaining a sample and a good supply of clean water is very much crucial to civilization. Now, to understand the chemistry that occurs in diverse places like the human body or the atmosphere or in groundwater or even the ocean or local water treatment plants, etc., we have to understand how substances dissolved in water react with each other. However, before we can understand solution reactions, we very much need to discuss the nature of solutions in which water is the dissolving medium or solvent. These kinds of solutions are what are called aqueous solutions. Now, water is one of the most important substances on Earth. It is essential for sustaining the reactions that keep us alive, and it very much affects our lives in many direct and indirect ways. One of the most valuable properties of water is its ability to dissolve many different substances. What happens when a solid dissolves in water? Now, to understand that kind of process, all right, we need to consider the nature of water. Liquid water consists of a collection of H2O molecules. An individual H2O molecule looks like this, and it has this bent or V shape, right? Where there is an angle between the hydrogen-oxygen-hydrogen connection we see here. The angle between this is about 105 degrees. Now, this HOH bond in the water molecules, this is covalent bonds that are formed by electron sharing between the oxygen and the hydrogen atoms. However, the electrons of the bonds are not shared equally between these atoms. Oxygen is more electronegative. It enjoys electrons more than the hydrogens do, so it pulls those electrons a little bit more towards itself. And what this results in, since the oxygen is slightly pulling on those electrons a little more, is now we have a partial negative charge on the oxygen, and we have partial positive charges on the hydrogens. Because of this unequal charge distribution, water is said to be a polar molecule. It is this polarity that gives water its great ability to dissolve compounds. Now, in addition to that, water molecules are also known for their strong intermolecular attractions. These attractions occur between the slightly negative oxygen atom of one water molecule and the slightly positive hydrogen atom of another water molecule. There is this interaction between these two water molecules that extends to many more water molecules as well. This unique interaction is known as hydrogen bonding. This is a type of dipole-dipole attraction that we're going to talk about much later on. But it is this strong hydrogen bonding that gives water its unique properties, like its very high heat capacity and, you guessed it, its ability to act as a solvent for many substances. And so what you have here is the positive ends of the water molecules are attracted to the negatively charged anions, and the negative ends are attracted to the positively charged cations when we start to think about water interactions with ions. And this process is called hydration. So that was kind of a fun fact. What is really happening here if we dissolve ionic compounds in water, right? Now that we know a couple of things, we know that our water molecule is partially charged. We have a partial negative charge on the oxygen, partial positive charges on the hydrogens. One hydrogen water molecule can interact with other water molecules through hydrogen bonding. And then these partial charges can then interact with other kinds of charges. And this is really important because now we want to talk about what if we dissolve ionic compounds in water? Well, the hydration of these ions are going to cause a salt to fall apart in water, or in other words, to dissolve. The strong forces present among the positive and negative ions of the solid are replaced by strong water ion interactions. So if we try to dissolve salt in water, say sodium chloride, what's going to happen is that the negative parts of the water molecule, this partially negative oxygens of our water molecules, are going to surround our sodium cation. They're going to hydrate this sodium cation with the oxygens facing towards this sodium cation. What about the anion of this sodium chloride? It's also going to be surrounded by water, but here the hydrogens with the partial positive charges are going to face towards this negative anion. And so we get this kind of dissolving of the salt in water. Now, the solubility of ionic substances in water varies greatly. So, for example, sodium chloride is quite soluble in water. But if you take something else like, say, silver chloride, it's only very slightly soluble. And the differences in the solubilities of ionic compounds in water, that typically depends on the relative attractions of the ions for each other versus the attraction of the ions for water molecules. So there's this sort of competition, sodium chloride attractions versus sodium and water, and chloride and water interactions. And those kind of have a bit of a competition going on, hence why the solubility of ionic substances in water varies greatly. Now, solubility is very much a complex topic, and we're going to get into it a little bit in this chapter and a little bit more in later chapters in general chemistry. But even then, I want to state that there is so much that goes into talking about solubility. But with that, we've covered everything in this first objective, and now we can move into our second objective. The second objective is on the nature of aqueous solutions. Now, a solution is a homogeneous mixture containing two or more substances. Each substance in a solution is uniformly dispersed as separate atoms, molecules, or ions throughout another substance. Now, we usually find it useful to describe a solution in terms of one or more solutes dissolved in solvent. The solvent is the component that determines the phase of the solution. Any other component is described as the solute. Now, if we're thinking about solutions, solvation is an important part of kind of capturing that idea. Solvation is the electrostatic interaction between solute and solvent molecules. This is also known as dissolution. Now, it can sometimes be referred to as hydration when water is the solvent. Now, solvation involves breaking intermolecular interactions between solute molecules and between solvent molecules, and then forming new intermolecular interactions between the solute and the solvent molecules together. Something else we want to be able to know is how much solute is going to be able to dissolve into a given solvent. And so the solubility of a substance is the maximum amount of that substance that can be dissolved in a particular solvent at a given temperature. Now, when we're talking about solubility, there's going to be different levels, all right? So we can talk about a saturated solution, an unsaturated solution, and a supersaturated solution. So let's go over these terms. When this maximum amount of solute has been added, the dissolved solute is in equilibrium with its undissolved state, and we say that the solution is saturated. If more solute is added, it will not dissolve. An unsaturated solution is a solution that contains less solute than the maximum amount that the solvent can dissolve at that specific temperature. In other words, you can still add solute and more solute can still be dissolved without needing to change any other parameters to make it happen. Then we have supersaturated solution. This is a solution, this is a state of a solution that contains more of the dissolved material than could be dissolved by the solvent under normal circumstances. So it can also refer to a solution that has been forced to contain more dissolved substances than it would normally allow at a given temperature. And this is usually achieved by dissolving the solute in one condition and then slowly changing it without triggering any release of the solute to kind of maximize this amount of solute dissolved in solvent. Now, with those definitions out of the way, we're going to move into a conversation about electrolytes. Substances that form ions in aqueous solutions are going to conduct electricity. If we want to discuss how substances conduct electricity, we want to define what an electric current is. An electric current involves the flow of charge, which is why we can say that substances that form ions in aqueous solution will conduct electricity. It is because there is this flow of charge, cations and anions. Now, if the solution in the container conducts electricity, the bulb lights up, right? Especially if you're doing a quick little test to see if electricity is conducted or not. Pure water, this is not an electrical conductor. However, some aqueous solutions will conduct current very efficiently, and if that's the case, then in your experiment, the bulb will shine very brightly. When this is the case, what you have is a strong electrolyte. These solutions contain strong electrolytes. Other solutions, they might conduct only a small current and the bulb may only glow dimly. These solutions contain weak electrolytes. Some solutions are going to not permit current to flow at all, and the bulb is going to remain unlit. These kinds of solutions contain non-electrolytes. Now, the obvious next question then is what forms ions? There are two important principles that are going to be helpful in understanding aqueous solutions. First, when ionic compounds dissolve in water, they're going to dissociate into ions. Now, we know ionic compounds are made of ions, cations, and anions. Therefore, soluble ionic compounds will dissociate into ions, and these charged ions allow the aqueous solution to conduct current. The second thing we need to know is that some molecular compounds also form ions when dissolved in water. This is a process called ionization. So, this is the idea behind what forms ions. So with this, an electrolyte is a substance that conducts electricity when dissolved. And since an electric current can be conducted anytime there are ions dissolved in aqueous solution, any substance that forms ions when dissolved in aqueous solution is an electrolyte. But then the question becomes, well, what is this range that we categorize this electrolyte? Is it a strong electrolyte or is it a weak electrolyte? So that's what we want to talk about next and begin to kind of learn how to distinguish between strong and weak electrolytes. A substance that completely dissociates into ions in aqueous solution is called a strong electrolyte. Here, for strong electrolytes, there is 100% ionization. All right, so the principal species are the ions of the electrolyte in the solution. What this results in is high electrical conductivity. And you can identify a strong electrolyte by knowing this fact. Strong electrolytes are strong acids, strong bases, and salts. And we're going to cover these classifications in a little bit, so hold on. Now, what about weak electrolytes? Some electrolytes are weak electrolytes. They will only partially ionize in aqueous solution. So that means there's about 1 to 10 approximately, this is a rough approximation, ionization that happens. And the principal species is the ionized electrolyte itself. What this results in is low electrical conductivity. And you can identify weak electrolytes as weak acids, and weak bases. Now, we also can't forget about our non-electrolyte category. Just to reiterate, non-electrolytes are molecular compounds that dissolve in water without forming ions. Since non-electrolytes do not form ions in solution, obviously they don't conduct electrical current when dissolved in water, because our very definition was that for us to have an electrolyte solution, we have to form ions, and we have two means of that. When ions are not formed in solution, then what we're dealing with is non-electrolytes. All right. So, two important classes of non-electrolytes are sugars and alcohols. And with that, we have completed objective 2, and we can go ahead and move into objective 3, composition of solutions. Chemical reactions often take place when two solutions are mixed. To perform stoichiometric calculations in such cases, we need to know two things. One, the nature of the reaction, which is going to depend on the exact forms the chemicals take when dissolved. And two, the amounts of chemicals present in the solution, usually expressed as concentrations. Now, the concentration of a solution, it can be described in many different ways. At this point, we're going to consider only the most commonly used expression of concentration, molarity. Molarity is defined as moles of solute over liters of solution, or volume of solution in liters. So we can simplify moles of solute to N and volume of solution as V. So molarity M is equal to N over V. This is the definition of molarity. And chemical laboratories, they often purchase concentrated solutions, which then have to be diluted prior to use. And so these concentrated solutions are called stock solutions. They take up less room in a chemical stock room than more dilute solutions containing the same amount of solute. And so, knowing what we know now about how we define molarity as the moles of solute over the volume of solution, the liters of solution, and also the fact that in a chemical inventory, you want things to take less space, so you buy concentrated solutions that need to be diluted. How do we reconcile these two ideas in order to dilute a solution to a different concentration? Well, dilution, this is a very important process in chemistry, especially when you're preparing solutions for experimental procedures. And what it involves is adding a solvent, usually water, to a concentrated solution to decrease its concentration. Remember, molarity, this is the number of moles of solute per liter of solution, and it is the standard unit of concentration in chemistry. When a solution is diluted, the total amount of solute in moles remains constant. But what changes is the volume of the solution. It increases, resulting in a lower molarity. And so, chemical labs usually buy very concentrated solutions here. All right. Then they add a solvent so it's diluted. Your N stays the same, but what changes is your volume. Here you have a lower volume, and then when you add more solvent, now you have a higher volume. If molarity is defined as moles over volume, what you notice is that molarity and volume are inversely related. If you increase volume, you decrease molarity, hence, you decrease concentration. So, again, when a solution is diluted, the total amount of solute in moles remains constant, but the volume of the solution increases, resulting in a lower molarity. Now, the process of dilution can be mathematically described by this equation that you see here. Molarity of the concentrated solution multiplied by the volume of the concentrated solution is equal to the molarity of the diluted solution multiplied by the volume of the diluted solution. You might hear it as, it's shortened as M1V1 equals M2V2. This is the same thing. We're just giving 1 to the concentrated solution and the number 2 to the diluted solution, and this just makes it easier to remember. M1V1 equals M2V2. M1 and V1 are the molarity and volume of the concentrated solution before dilution, and M2 and V2 are the molarity and volume of the solution after dilution. This relationship shows that the product of the initial concentration and volume is equal to the product of the final concentration and volume. And this principle is extremely important because it ensures the conservation of the number of moles of solute during the dilution process. Also notice that when a solution is diluted, the volume changes and the concentration changes. But again, I need to reiterate that the number of moles of solute does not change because the only thing we've done is added more solvent. This makes more sense when we begin to tackle some practice problems. So let's do a couple together. This first problem says, what is the molarity of a solution that has 25 grams of glucose? And we're given the molecular formula C6H12O6, and we're given the molar mass of glucose as 180.2 grams per mole, dissolved in enough water to have 125 milliliters of a solution. Again, the goal is to figure out what is the molarity of a solution that has 25 grams of glucose and dissolved in enough water to have 125 milliliter of solution. Okay, so what we need to do is remember that molarity is moles of solute over liter of solution. All right, that is our definition. What we're given is grams of glucose, and then we're given milliliter of solution. So we're going to have to do a couple of things here. First thing is we need to figure out the number of moles of solute. And we could do this very easily. We're given the grams of glucose, 25 grams of glucose, and we can convert that to moles by just multiplying by the molar mass, which we're also given, 180.2 grams per 1 mole. This is going to give us about 0.139 moles of glucose. Beautiful. Now we also need a second thing. We need our volume of solution in liters. We have 125 milliliters of solution. We want to convert that. We want to convert that to liters. We know that there is 1,000 milliliters per 1 liter. And what this is going to give us is that we have 0.125 liters. Now, all we have to do to figure out the molarity is plug those back into our equation for molarity. We need to have moles, 139 moles of glucose over liter of solution, which is 0.125 liters. This gives us our molarity. Our molarity is going to be equal to, if you plug this into a calculator, 1.11 molarity for our glucose solution. And there you have it. That's how we approach this first problem. All right, let's do another one. How many grams of sodium chloride are present in 86.2 milliliters of a 0.275 molar sodium chloride solution? Okay, this is very interesting. What are we given? We're given the molarity. We're given the volume. We want to figure out grams of sodium chloride, which we can only do if we already have moles of sodium chloride. So let's write our definition. Molarity is equal to moles over volume. The first thing we want to do is obviously solve for moles. We want to solve for N. So how are we going to do that? We're going to multiply each side by volume. This way, volume cancels out on this side, and moles equals molarity times volume, both of which we have. All right, we have the molarity, that's 0.275 molar of sodium chloride, and we have the volume in milliliters, which we can easily convert to liters by doing the same kind of step here. Here's a quick hint. You can also just move the decimal 1, 2, 3 positions to get the liters. All right, so 86.2 milliliters is equal to 0.0862 liters. We multiply this to get moles of sodium chloride. If you plug this into a calculator, you'll get 0.0237 moles of sodium chloride. Beautiful. Now what we can do is take moles of sodium chloride and convert it to grams of sodium chloride just by multiplying by the molar mass of sodium chloride. By the way, the molar mass of sodium chloride is 58.4 grams of sodium chloride per 1 mole of sodium chloride. You can figure this out by figuring out what the mass of sodium is on the periodic table and chloride and simply adding those up. Now we have our moles that we calculated of sodium chloride. All right, moles of sodium chloride. We're going to multiply it by this molar mass, so moles of sodium chloride cancel out, and we're going to get our final answer in grams. If we plug this into a calculator, we're going to get 1.39 grams of sodium chloride. Wonderful. So now we've done 2 problems where we are using or manipulating our formula for molarity. Molarity is equal to moles over volume. So we've done 2 problems here. Now let's also do a problem where we're doing dilution. All right. So this problem says, suppose you have a stock solution of 12 molar hydrochloric acid. How would you prepare 250 milliliters of 0.1 molar hydrochloric acid? All right, so you're starting off with a scenario. And that scenario is that you have 12 molar of hydrochloric acid. This is your molarity of your concentrated solution. And now what you want to do is you want to take that very concentrated solution and you want to prepare 250 milliliters of a less concentrated solution. So this is your molarity of your diluted concentration. And you want exactly 250 milliliters of that. So this is your volume of your diluted solution. What you're trying to figure out is how would you prepare that? So in order to be able to prepare that, what you're missing is figuring out what your volume of your concentrated solution is. Because then what we can do is use our equation, mole concentrated multiplied by volume concentrated equals molarity of your diluted multiplied by your volume of diluted. Right? This is just the equation we just talked about. We have this, and we have this. All we need to figure out is this to be able to know how we can prepare 250 milliliters of 0.1 molar hydrochloric acid. So what we're going to do is we're going to divide both sides by M concentrated, the molarity of the concentrated. All right. And now we have an equation where we can solve for the volume of the concentrated solution. Molar of the diluted multiplied by the volume of diluted, all divided by the molarity of the concentrated, M of the concentrated. We have all of these values. Now, here's a cool thing. We have our volume of diluted in milliliters. Traditionally, when we talk about molarity, we say it's moles of solute over liters of solution. But here's a fun fact. We don't have to convert this to milliliters. All we have to remember is that if we keep VDIL, right, volume of diluted in milliliters, that means our answer, volume of concentrated, is going to be in units of milliliters. So just remember that. Okay, so now we're just going to go ahead and plug things into this equation. All right, volume of concentrated is equal to the molarity of the diluted solution, which is 0.11 m. All right, multiplied by the volume of diluted, that's 250 milliliters. That's going to be all divided by the molarity of the concentrated solution. That is going to be 12 molar. Notice how molar cancels out. We're going to get our answer in units of milliliter. Plug this into a calculator, and what you get is 2.08. So what you're going to need is 2.08 milliliters of your 12 molar of hydrochloric acid. All right. To be able to prepare 250 milliliters of 0.1 molar hydrochloric acid. So what that means is this is how you're going to prepare this diluted solution. Now, just a fun fact, you never add water to a concentrated strong acid. So instead, what you're going to do is you're going to begin by placing water into a 250 milliliter volumetric flask until it's approximately half full. And then you're going to use a pipette. You're going to measure out 2.08 milliliters of that 12 molar hydrochloric acid. You're going to begin to add it carefully to the water in the volumetric flask. And then after you've done that, you can then slowly add more water to the volumetric flask until the bottom of the meniscus is located at the calibration mark on the volumetric flask. And that is how you can begin to prepare 250 milliliters of 0.1 molar hydrochloric acid from your 12 molar hydrochloric acid. Remember, you are diluting with water. Fantastic. So there you have it. We've solved 3 example problems for that objective. Now we can move into our 4th objective. Our 4th objective is titled Types of Chemical Reactions. To make sense of all these reactions that we're going to cover, we need some system for grouping reactions into classes. And while there are many different ways to do this, we're going to use a system that's most commonly used by chemists. Here we see that we have 3 categories. We have precipitation reactions, acid-base reactions, and oxidation-reduction reactions, also known as redox reactions. Now, we're going to talk about these first 2 in this chapter. We will also have chapters later down the line where we focus even more on acid-base reactions, and other chapters down the line where we introduce redox reactions as well. Now, with this introduction, we're going to go ahead and end this first part of chapter 4. And in the next part, we're going to go ahead and start with a discussion on acid-base reactions. I hope this video has been helpful so far. Let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.